Welcome to today's webinar titled Satellite Ephemeris Parameterization Methods to Support Lunar Positioning, Navigation, and Timing Services, based on a paper published in the winter 2024 issue of Navigation, the Journal of the Institute of Navigation. This paper can be accessed from the Navigation Open Access website at navi.ion.org, where you can read, download, cite, and share this article and many others. Today's webinar is being presented by Keidai Iiyama. Keidai Iiyama is a PhD candidate in the Department of Aeronautics and Astronautics at Stanford University. He received his ME degree in aerospace engineering in 2021 from the University of Tokyo, where he also received his BE in 2019. His research is on positioning, navigation, and timing of lunar spacecraft and rovers, and systems designs for lunar navigation systems. Today's webinar is being recorded and will be available on our website, YouTube, and other social media channels. Following the presentation, we will accept questions from the audience. You can submit your questions by selecting the Q&A button in your viewer. Now, thank you for joining us. We will turn the time over to Keidai.
Okay, thank you for the kind introduction. So I'm Keidai Iiyama. I'm a PhD candidate at Stanford University, and today I'll be presenting about satellite ephemeris parameterization methods to support lunar PNT services. So the first author was Marta, but today I'll be presenting on behalf of Marta. Okay, so in the last decade, we have entered a new era of space exploration, with a particular emphasis on the lunar landscape. And this time, the goal is different from the Apollo era, which is the goal is to establish a permanent human and robotic presence on the moon and around in the lunar orbit. Some of the capabilities that are necessary for the success of these future missions include spacecraft nav and comms, precise landing, crew operations, autonomous rover mobility, far-side accessibility, and also scientific data return. And all of these capabilities are enabled by precise, reliable, and absolute position, navigation, and timing. So in order to meet this need for lunar navigation, NASA, ESA, and JAXA have joined together to develop a satellite-based solution for lunar PNT, which is called the LunaNet. The LunaNet is a network of cooperating satellite networks providing PNT and comm services. And this includes the space segment, which is the orbiters broadcasting PNT radio signals, a control segment, which is some ground stations or some control stations monitoring the system and providing user services, as well as the user segment, which is the user on the lunar orbit or on surface. And the important aspect about this is that the satellites that are part of this network broadcast a navigation message to users for localization. And this message includes what is called the satellite ephemeris, which are the parameters representing a satellite state in orbit. So users use these broadcasted parameters to compute the satellite positions whenever they want to localize. However, it is not possible to perfectly parameterize a satellite orbit without error. So this ephemeris errors will be part of the signal in space error, which will be kind of propagates to the user positioning error. So therefore, the important part about this satellite ephemeris parameterization is to minimize the user positioning error. This ephemeris parameterization must be a precise representation of the satellite orbit. And here we list some of the ephemeris design models that have been implemented or have been proposed for satellite-based PNT systems on terrestrial satellite-based navigation systems. So we noticed that there are models based on orbital elements. Some of them use numerical propagation or Cartesian state interpolation or extraporation. However, all of these proposed methods for terrestrial-based PNT systems cannot be directly applied to the LunaNet architecture because they operate on different dynamics assumptions or like orbit shapes assumptions. So here, there are like 3 challenges when we try to do the ephemeris approximation for lunar scenario that we're interested in. The first consideration or the challenge we have to consider is that we have to comply with the various lunar orbits that have been considered for lunar navigation, which has completely different shapes and dynamics conditions. For example, these orbits include the low lunar orbit, which are like it's kind of like a polar orbit that is close to the lunar surface, as well as elliptical lunar frozen orbits, which are more elliptical orbits that have longer orbital periods and it's farther from the moon. And just to emphasize this, design ephemeris model have to kind of comply with these different orbit shapes. So this is a significant challenge in the lunar ephemeris design. And another consideration or the challenge involves orbital perturbations. So ephemeris parameters must be able to capture these varying dynamic environment that a satellite experiences while it's orbiting in this lunar orbit. So specific to lunar orbits, the satellite experiences a weaker central gravity from the main gravitational body, which is the moon, compared to Earth. And it also experiences significant third body influences from the sun and the Earth, as well as solar radiation pressure. So also these dominating perturbation changes within the orbit in elliptical orbits. So near the Pelemoon, we experience high order like lunar gravity would be like kind of the dominant perturbation force. On the contrary, on the Apollon, there will be stronger third body perturbations and solar radiation pressure that will be more dominating perturbation force that will be acting on the spacecraft. So we need to our ephemeris model has to be capable of modeling the orbit precisely in both these two different domains within the orbit. And finally, the ephemeris parameters we design must meet the certain performance requirements. First requirements is the signal in space error, which is the instantaneous difference between the true and predicted satellite state in the orbit. So NASA, for its constellation, has established the following SISC requirement, which is the 13.34 meters 3 sigma for position, and the velocity is 1.2 millimeter per sec for 3 sigma. So this is a pretty strict requirement, and this ephemeris approximation should not exceed these SISC requirements. Another performance metric is the approximation interval or the update interval. So this is kind of the length of the time which the optimized parameter or the ephemeris parameter is valid without being updated. So we want to make this as long as possible in order to avoid having the system have to like update the ephemeris parameters very frequently. So we want to make this longer as possible. And the another important metric is the message length. So this is depending on the parameter we use, we might need a larger message length to be broadcasted to the user. And we want to make this as short as possible so that the user would need a shorter time to decode this entire ephemeris message. So the research objective is to develop an ephemeris approximation framework considering these three challenges. Particularly, we simulate the orbit of interest in a high fidelity orbit propagator, as well as build ephemeris models that is representative of this dynamic environment. And we want to evaluate the model performance based on the SISC and the approximation interval, as well as the message length. So in our approach, we first determined what kind of parameterization method to pursue between, especially if we are going to pursue an orbit element approach or a Cartesian-based model approach. So in this work, we decided to go for the Cartesian parameterization model. And the reason for this is that the orbit element-based model carries assumption that the OE vary by small amounts throughout the approximation interval. And this assumption did not apply well in the lunar environment where there is strong perturbations compared to the Earth. And also the orbit is elliptical. So there was a challenge on fitting this on the orbital elements. So we decided to go for the Cartesian approach. And based on this, the problem formulation would be to come up with a ephemeris model that minimizes the error between the predicted and the true ephemeris. And we also want to leverage the known SIC constraints in our problem. So we decided to formulate this problem as a constraint convex optimization problem, so that to ensure that these SIC constraints are satisfied within the fitted ephemeris. What we didn't model in our current work is that we didn't assume the clock offset and the clock drift. So this clock synchronization and clock estimation as well as time synchronization is left for future work. So here we also list several related works. So they're having a couple of like 2-3 works related on the lunar ephemeris. And the main difference compared to the other works are that we consider 2 different orbits, ELFO and LLO, and we formulated our problem as a convex optimization problem with constraints to enforce the constraint satisfaction, as well as we investigated the parameters in varying starting epochs, which is the true anomaly in this case to evaluate the performance at different places in the orbit. Okay, so we've go over this background and motivation. So next we would like to talk more about our lunar satellite ephemeris design and some performances that we've obtained. So first, I want to review about the problem formulation. So consider we have this blue true orbit that is represented in this blue line. And then in our method, we develop some approximation model and estimate this blue orbit using some fitted ephemeris, which is shown in this orange line here. In this orange line, we can also apply the constraints, which is shown in this red points here in this line. And then by solving this constraint optimization problem, we obtain a parameter set alpha, which is a vector of parameters that we get that represents this orange line, that is the fitted ephemeris. And the goal is to find this optimal basis parameter set alpha that minimizes the errors between the predicted and true ephemeris. And we have to do this, since we did for the Cartesian frame, we have to do this for the x, y, z coordinates. Each of them we have to optimize the parameter for each of them. Note that we are fitting the orbits in the inertial frame of reference. So we obtain a parameter set that can be shared with the position and velocity. So we just need to solve like 3 problems, each for the x, y, z, and x, y, and z. And for the surrogate models that we use to fit the ephemeris, we consider 2 different types, which is the polynomial basis and the Chebyshev polynomial basis. A polynomial basis is a rather simpler approach, and it's more computationally efficient. In terms of Chebyshev, it's a more recursive approach. And then this Chebyshev polynomial is usually used to represent planetary ephemeris. And for the sampling strategy, on where to sample these points to fit these points, we use what is called the Chebyshev-Lobato nodes. So this samples more nodes near the endpoints where it tends to have like larger deviation from larger fitting errors. And what is important here is the basis order n. This determines the accuracy of the fit, or like the resolution of the fit we can get, as well as but there's a cost of increasing n, which is it will result in increasing the computation and also the parameter set size. So it will lead to increased message size as well. And in addition to this fitting in the inertial frame, we want to convert them to the moon-centered moon-fixed frame, because what we are interested is the navigation of the lunar surface users. So in addition to the ephemeris in the inertial frame, we would want to provide them the parameters to convert the satellite orbits into the moon-centered moon-fixed frame. And we do this by providing a 313 Euler angle that converts the orbits from the inertial frame to the moon-centered moon-fixed frame. And what we observed that these angles kind of change linearly in the short period of time. So we assume that we do like a linear approximation And then we solve for these 6 parameters for the inertial to Euler angles. So it's for the Euler angles and its rates. So we solve for the 6 parameters to do this. To summarize, this is like the entire pipeline of our framework. So we first propagate the true lunar orbits, and we set up the optimization problem both for the satellite ephemeris fitting in the inertial frame and also the Euler angles. And we solve these parameters using CBXPy as a constraint optimization problem. And then based on that, we evaluate the performance metrics, which are the SIC, the parameterization interval, which is the maximum interval that the ephemeris can satisfy the SIC constraint, as well as the message length. Here, what we want to know that we evaluated the SIC in the moon center moon fixed frame. So this error would represent the errors coming from both the inertial orbit fitting error and also the Euler angle fitting errors. And also for the orbits, we assume 2 different orbits, the low lunar orbit and the UFO. And for parameterization, we tested different fit intervals and the starting point, which we call the initialization point, or and just to show one example, for example, we could test, like, we start from the uploon and then test for fitting for like 0.5 orbits. Like, so we did not only for the uploon, but 30 different starting points on the orbits, as well as different intervals, not only 0.5, but like different fit intervals to test how well we can fit these Ephemeris models. Going to the results, this table shows the results for the 3 sigma SIC positioning errors, both for the EFO and the LLO. It's not shown here, but we noticed that the polynomial and Chebyshev models provide feasible solutions for both orbits, and it has nearly identical SIC performance. And then also we observed that the solutions we obtained do not exceed the total SIC budget that is enforced by NASA. This is a good. This indicates that our methods can successfully optimize the Ephemeris parameters. We noted that the polynomial and Chebyshev had the similar errors, but the Chebyshev has an advantage in terms of the message size. Due to its recursive nature, Chebyshev can approximate the orbit with like smaller number of parameters compared to the polynomial. If we are using the same basis order. This is an advantage of using the Chebyshev model, but it also requires more computation. So this is kind of the trade-off between the two fitting methods. And finally, we want to show the coverage analysis. So this shows how much was our method able to kind of fit the orbit, how were the methods able to fit the orbit when we start from different true anomalies. So first thing we observed that near the true anomaly of 180, which is near the apolloon, we are able to fit longer orbits, which means that it is kind of easier to fit the orbits near the apolloon. This is because near the periloon, the satellite experiences more faster motion, so it is faster that the orbit would start deviating from this predicted orbit. So it's easier to near the periloon, we need to update the Ephemeris parameters more frequently compared to the apolloon. So this is a challenge that is in the lunar. Also, we obtained a similar train when comparing ELFO and LLO. Because LLO is closer to the lunar orbit, we also have to update the parameters more frequently compared to the ELFO. So we can only approximate around like 10% of the orbit in LLO, and we need to update the parameters more frequently. Yes, so we would like to summarize our findings. So we kind of tackle the problem of PNT message, the ephemeris fitting problem in the lunar navigation satellites. approach was to test out Chebyshev and polynomial bases to directly fit Cartesian states and enforcing SIC constraints by solving a constraint convex optimization problem. The result, we got feasible solution for LLO and both EFO. The fitting interval that we can get was around 0.3 or like under 0.3 orbit in LLO and around half orbit for EFO. And we needed higher order parameterization and shorter updates frequency in EFO Pelilun and LLO. And Chebyshev models provide advantages in terms of message length. In terms of code availability, we made this code open in our in-house simulator LUPNT. So this LUPNT simulator is currently under development. It's a C++ based Lunar PNT simulator with Python interface, capable of conducting multiple simulations related to Lunar PNT, including orbit propagation, side-lobe GPS simulation, some basic orbit determination, as well as involving like crosslinks between satellites. So we're modeling these features in our simulator, and we added this ephemeris fitting feature as well in our simulator. So if you're interested, please check out. It's currently under kind of like a features branch, but we are planning to merge it to the main development branch sooner. So yeah, please stay tuned for it. And for future works, we are considering, since we kind of noticed that we need a pretty frequent update in order to comply with the NASA SIC standard near the Pendulum and also in low lunar orbit, we're considering to combine this onboard orbit determination methods and with this ephemeris generation so that we could potentially update this ephemeris online on board the spacecraft so that we can have accurate ephemeris presentations more frequently without ground intervention. So this is what we're trying to do as a future work. Also, we are working on implementing this end-to-end simulation of the lunar navigation constellations, spanning from space segment, control segment, and user segment. So starting from the orbit determination, applying this ephemeris fitting approach, and also modeling this broadcast of the signals and then user positioning algorithms on the lunar surface. So we are planning to implement this on LUPNT so that you can run the entire simulation and verify your constellation performance. Yeah, thank you. That's all. Thank you very much for attending my presentation.
Thank you for this great presentation. We will now accept questions from the audience. So as a reminder, you can submit your question using the Q&A button in your viewer. And it looks like we already have some questions coming through. So our first question for you is, have you looked at three-body orbits like NRHO?
Yes, thank you for the great question. We haven't actually looked at the NRHO fitting performance yet, but I would say our advantage of our approach is that it's based on Cartesian orbit elements, Cartesian states. So compared to like say orbit elements approach, we can also apply these methods for three-body orbits like NRHO or like hello orbits. The potential challenge that we can experience in NRHO is because the orbit is very large and it's very elliptical. We have very different dynamics conditions comparing the periapsis and apopsis. So coming up with a parameter that can kind of fit both conditions at the same time might be more challenging compared to the UFO. But yeah, we are looking this in the future. Yep.
Okay, and looks like we have an anonymous question.
Mhm.
Are you able to provide a finer breakdown with how you calculated message size?
Yes. So if you can see this slide, we kind of computed the message size by discretizing the kind of computing how well we need to discretize this parameter for each parameter that we broadcast. So we set it like a the kind of like the discretization error that we need in order to do this performance, and then we basically compute it based on the message size, how much message size we need to broadcast. For the very much the details, you can look in the paper, and then we have more details on how to compute this.
Okay, next question. Can
Mhm.
you elaborate a bit more on the SISE budget?
Mhm.
Can you, they have a little bit in here. Can you elaborate more on the SISE budget? They're assuming that the NASA requirement on this includes both ephemeris fitting error as well as the actual satellite position and clock
Yep.
errors. So can you kind of elaborate on this
Yeah,
budget?
yeah, yeah. So I think it's a good point. So in our research, we assume that we can use this entire budget for the ephemeris fitting, but actually it's not true. We have to account for the orbit determination error, actual orbit determination error, plus the ephemeris error. So in this research, we just use this entire budget for only the fitting. But in reality, we need a more tighter bound on the ephemeris. We need to allocate a more tighter bound on the ephemeris. Oh, sorry. I think in this research, we kind of assume that we can use up to like the 3 sigma. Oh, wait. Oh, no, no, no. I think that's right. We kind of assume that we can use this full budget. But in reality, we need to make this bounds tighter in order to consider the navigation errors that will be actually coming in, and also other sources of error maybe that could be coming in. I presume there's like less atmospheric errors, but maybe some multipath errors could come in. Other satellite clock errors can come in as well. Like so, yes. In the future work, we're planning to develop this entire pipeline to actually determine like what the whole error would be, whole SIS error would be, considering both orbit determination and parameterization. And I hope this answered your question. Yep.
Okay, looks like we have one more question.
Hmm.
When developing your approximations for the ephemerides, what is considered as the truth data are these sensor measurements?
Yes, I think so. In this research, we just use this true data as the true propagated orbit. So in reality, that the fitting error, the fitting has to be performed on the estimated orbits based on orbit determination using some sensors measurements. But in this research, we just assume that the fitting error um, with respect to the true orbit that we propagated. So related to the past question, um, in to evaluate the real SIC error, we need to add up the actual orbit determination error and also the ephemeris fitting error that is fitted on this estimated orbit. So that's what we are planning to do in our future work. Yep.
Great. Well, thank you. That is all. Thank you to
Mhm.
everyone for joining us for today's webinar. And thank you, Keidai, for your presentation.
Mhm.
We want to remind everyone that a recording of this webinar will be posted to our website, YouTube, and social media channels by Friday the 22nd, so this Friday. And thanks again. We look forward to having you join us at a future ION webinar.